Today we'll look at 10 of the most interesting algorithms ever engineered, and how they're used to solve very interesting problems in the real world. First on the list, we have wave function collapse. One of the weirdest things in all of science is the double slit experiment, where particles behave like a wave when you're not looking, but when you look, they suddenly collapse down to a particle. It seems counterintuitive, but it makes total sense when you realize we're living in a simulation, and the universe wrote this algorithm to cut down on its AWS bill. Speaking of which, AI is weird as hell. Diffusion is a machine learning algorithm, originally developed at OpenAI, and is the magic behind image generators like DALL-E and Stable Diffusion. But the concept of diffusion actually comes from thermodynamics, where particles spread from areas of higher concentration to lower concentration. In artificial intelligence, the process is reversed. The algorithm starts by generating random noise, which would be like high entropy in thermodynamics, and gradually refines it to a structured image, which would be lower entropy. But now let's talk about simulated annealing. Annealing is a word that comes from metallurgy, where metals are heated up and cooled down over and over again to remove defects. The same idea is used in optimization algorithms to find the best answer in a sea of good answers. And the most ingenious sorting algorithm of all time is without a doubt sleep sort. Here's what the code looks like in Bash. It's incredibly simple. It loops over the array, and then for each element, it opens up a new thread that sleeps for the amount of time proportional to the value of its element. Then finally, after waking up, it prints that element. Speaking of which, you might be familiar with another useless sorting algorithm, BOGO-sort, which tries to sort an array by randomly guessing over and over again. It's like playing the lottery. But one of the most practical and goated algorithms of all time is RSA, a public key crypto system. It's essential for digital security, allowing people on the internet to lock their mailboxes and sign their letters with a unique signature. At the beginning of this video, I mentioned the marching cubes algorithm, but it deserves a closer look. So first, we start with a 3D scalar field, which might represent data from an MRI machine. Each point in the 3D space is represented by a single number or scalar. The algorithm starts with a single point, then takes its 8 neighboring locations to form an imaginary cube, but treats the 8 values as a bit in an 8-bit integer. This results in 256 different possibilities, which point to a pre-calculated array of polygons. In modern times, though, we're often dealing with distributed systems in the cloud, and that brings us to the Byzantine generals problem. It works by having a node broadcast a pre-prepared message to other nodes, indicating its readiness to execute some code that will change the system. The other nodes will respond back in agreement, then after a certain threshold, a consensus is formed. Once there's a consensus, the original node sends back a commit message to all the other nodes, which can then all execute the changes, making the entire state of the system consistent. What's really cool about algorithms, though, is that they can also reflect nature. In this case, the birdoids have 3 rules. They steer to avoid crowding, they steer towards the average heading of the flock, and they steer towards the center of mass of their local flock mates. The end result are these intricate patterns that weren't programmed directly, but just emerged naturally. But finally, that brings us to an old algorithm that blew my mind just the other day and inspired this video. Boyer-Moore string search. It's weird because it becomes faster and more efficient as the string it's searching becomes bigger. That seems impossible, but it makes sense when you understand the algorithm. It scans text from right to left, then has 2 rules. When it encounters a bad character not found in the search pattern, it jumps past it based on an estimation made in a pre-processed table. Likewise, if it finds a partial match, then a mismatch occurs. It has a separate pre-calculated table that maximizes the number of characters it can safely skip. These rules are called heuristics, which are like functions that are not guaranteed to be perfect, but are far more practical than looping over every single character.